Okay, so at the end of the last lecture, I had introduced to you the term surface tension, and also that surface tension is very easy to measure at an air-liquid interface, and very quickly introduced you to two ways that you could measure the surface tension with some not too difficult equipment or setup within a laboratory. So what we find is that surface tension will change if you add material to a surface. And we find that if you add something that likes to go to an interface, then surface tension will go down. And we saw that example when a surfactant, or I think some sort of detergent, was added to the surface where a pin was floating on the top of the surface of water. And then our surface tension went down because of the added detergent. Then the pin suddenly was unable to be held up by the water. And so the surface tension had dropped too low. So we know that you can add material to a surface that will significantly lower surface tension. But you can't add anything to a liquid that will significantly increase surface tension. So it will decrease surface tension, but never significantly increase surface tension. Okay, and the reason why is because, of course, surface tension is basically surface free energy. And so if there is a material that could go to the surface and increase the energy of the surface, you would be making that energetically unfavorable. And so that material would just prefer to stay within bulk solution and not go to the surface. Okay, so it's only going to go to the surface if it can reduce the energetics at the surface and thus reduce surface tension. So a good example there is water doesn't really like that interface between it and air because water can't hydrogen bond with air. And we showed how that led to unbalanced forces. Well, if you add something that is going to go to the surface that prefers to be at the surface than water, then the system overall is going to prefer that energetically. But you're never going to get an example where you add something that dislikes being at the surface more than water, so replaces a water molecule. That wouldn't happen. Okay. So this is a truth for all systems. When a substance dissolves in a liquid, the surface tension can decrease, but it will never significantly increase. So something that's going to make the surface tension decrease is a surface active agent or a surfactant. And they occur widely in nature, and they've been used for thousands of years in emulsifiers, in cleaning and in foods. So things like ice cream, milk, butter will all have surfactants in them. We can have natural surfactants such as proteins, and we can have surfactants in detergents. So there are many examples with surfactants in them. Molecules that are surfactants will have distinct regions within the molecule, with one region of the molecule being hydrophobic, so having functional groups that don't interact well with water, and they'll be stuck to another part of the molecule that will be very hydrophilic, so very polar and able to very easily interact with water. So surface active agent has the advantage of happily interacting with water on one end, but the other end being happy to interact with a phase that doesn't interact with water. So the simplest way of thinking about a surfactant, that is the way I'm going to show it in the lectures, is this molecule here. A standard surfactant molecule could have a hydrophobic hydrocarbon tail and a hydrophilic polar head group, and so that would have surfactant properties. what will a surfactant do in water? In water, the surfactant will absorb to the surface. It will go to the surface, preferably to staying in water. So it's still in water, but it'd be very happy to be at the surface. Okay, so that means it will replace as many of the water molecules that were at the surface as possible, because the surfactant will prefer to be there than the water molecule will. So the surfactant will prefer to be there because it has a hydrophobic part that doesn't really want to be in water, and a hydrophilic part that really likes to be in water, so interacts well with water. And so you'll find that surfactant molecules align at a surface so that the hydrophobic part sticks out and the hydrophilic part stays in the water. And if you pack the surface tightly enough, if you add enough to the water, you'll end up with a monolayer like this diagram here. Okay. There are a number of different types of surfactants, and they tend to be characterized based on the head group of the surfactant. So that's the hydrophilic part of the surfactant. Okay. The hydrophobic part of standard surfactants tends to be a hydrocarbon chain, and the hydrophilic part will be defined by whether it is charged or uncharged. So if it has a negative charge, and therefore it would have a positive counterion connected to it, such as your top example there, it will be an anionic surfactant. If it's positive charge, it's cationic. If it's polar but non-ionic, then obviously we call it non-ionic. And if the head group has a positive and a negative ion in it, and you can see this molecule here is a more complex molecule. The hydrophobic part of this molecule is the fused benzene, the fused rings that you can see there. And so that's the hydrophobic end of this molecule, and the hydrophilic end has these charged components. So it has NH, it has an N plus, and it has an SO minus there, and you can see it has a positive and a negative charge in that molecule. And so that molecule is zwitterionic in that its net charge is 0, but it contains within its head group both a positive and a negative charge. And that molecule is also a good example to show that surfactants are not always simple hydrocarbon chains connected to a head group. The hydrophobic part of the molecule can be quite complex, as well as the hydrophilic part of the molecule. So these are known as the classifications of surfactants. Now, the surface activity of surfactant will depend on the structure of that molecule. So it'll depend on how big the hydrophobic part of the molecule is compared to how big the hydrophilic part is. So in other words, how it's also linked to how soluble it is. Okay, so if the solubility is very high, you can imagine that it's got a much bigger hydrophilic part than hydrophobic part if solubility in water is very high. So obviously the surfactant, these properties within surfactant also have an impact on the solubility of our surfactant. Now, Trobe's rule is a rule for looking at a simple surfactant series where you have a basic hydrocarbon chain as your hydrophobic part of the molecule connected to a head group. And so you can change the properties of that surfactant just simply by changing the length of the hydrophobic part of the molecule, so the length of the hydrophobic hydrocarbon chain. And as you increase the hydrocarbon chain, then you're going to end up with a molecule that's more and more unhappy to be in bulk solution of water, and more driven to want to be at the surface. So if the hydrophobic part gets bigger, it's going to prefer to be at the surface. And so it's going to lead to changes in surface tension that depend on the length of that hydrocarbon chain. So Traub's rule says, for solutions of a surfactant series, the molar concentration required to produce equal lowering of surface tension of water decreases threefold for each additional CH2 group in the hydrocarbon chain. And that's a bit of a mouthful, so let's do an example to show you what that means. Here's my example. Think of an anionic surfactant. Okay, so that means it has charge and it has 16 carbon atoms in its hydrophobic chain. And it can lower the surface tension of water to 15 millinewtons per meter at a concentration of 8.4 times 10 to the minus 4 moles per decimeter cubed. Okay. So we can see that that is significantly lower than water would be. So the surfactant has effectively lowered surface tension. If you reduce the number of carbons in that hydrophobic chain from 16 to 14, then you're going to need a higher concentration of the surfactant to have an equal lowering in surface tension. So if you reduce the surfactant hydrocarbon chain to 14, you're going to need more surfactant to get yourself a surface tension of 15. Okay, how much more? Well, Traub's rule says you'll need 3 times more for each reduction in 1 carbon in the carbon chain. So 3 times more from going from 16 to 15, and then a further 3 times more. So that means total now 3 times 3, which is 9. So it's 9 times more for going from 16 to 14. So Traub's rule basically says take that concentration that you originally had, the 8.4 times 10 to the minus 4, and you'll need to multiply it by 9 to get to the concentration that you'll now need to use with this new surfactant if you want to get to a surface tension of only 15. So the answer to this question is to say the concentration required increases by 3 with each loss of carbon, and so it increases by 9 for a loss of 2 atoms. And so it's 8.4 times 10 to the minus 4 times 9. And so that gives you 7.6 times 10 to the minus 3 molar, which is moles per decimeter cubed, which could also be written as 7.6 millimolar. Okay, so that is the amount of the surfactant, this new surfactant with the smaller hydrocarbon chain that you would need to lower the surface tension to 15 millinewtons per meter. Okay, so I'll let you go through that example again yourself to make sure that you fully understand it. Now, I did show you an example of our zwitterionic surfactant that didn't follow the basic rule of a hydrocarbon chain connected to a hydrophilic head group as our surfactant. And drugs can also, and often are, surfactants themselves, so they will have surface active properties. If they have a region that is hydrophilic and a region that is hydrophobic, then they're going to have surfactant-like properties. And these two molecules here both have surfactant-like properties. They have a chain leading up to the amine, the tertiary amine, and that tertiary amine is the hydrophilic part, and then the ring part of the molecule is the hydrophobic part. And so they do have surfactant-like properties. And sometimes having a surfactant-like property can result in changing the overall behavior of the molecule, can impact its stability and other things within the molecule. Finally, I just wanted to highlight the many uses of surfactants, some of which we will come across in later lectures. But surfactants can be used for multiple different reasons in products because of the way they like interfaces. Okay, so surfactants, you'll often hear them being used to help wetting. So for wetting the surface of particles, by helping a liquid wrap around and interact with that solid surface. And they can also be used to improve emulsification by improving the interaction and the mixing between oil and water. They can be used for things like anti-static systems, lubricants, dispersing solids within a liquid or other phases within different phases, foams, and in also anti-foaming as well. So multiple examples, and there are such a wide number of examples of surfactants that I've just put a few pictures here of systems that are surfactant-based systems. So now you should be able to describe the term surface tension, and also we talked about methods that you can use to measure surface tension, and you should be able to explain why the surface tension of liquid of water is high, and also explain the effect a surfactant will have on surface tension, which we'll also cover a little bit more in the next lecture.